So let's say this is transformer A, this is transformer B, and this is transformer C. Okay. So primary of it is, let's say, A1 here, A2 here, and secondary of it is A1 here and A2 here. Similarly, B1 here, B2 here, C1 here, and C2 here. This is B1, small b1, small b2, C1, C2. Okay. So now this is, you have 3 single phase transformers, and as per your requirement, you can easily convert it into star-star connection, or you can convert it into star-delta connection, or delta-star connection, delta-delta connection. Okay, so different combinations of it is possible. Okay, let's try to make for star-star combination. Let's say the dot of these transformers are marked here, and the turn ratio of this transformer is, let's say, A:1, A:1. For each transformer, the turn ratios are same. Then obviously you will get similar voltage at the secondary of the transformer. If you energize the primary by equal voltages, the secondary will also be will have the equal voltage there. So let's say the dots are marked here. Here. Okay. Now let's say you want to make a star-star combination out of it. How to make it? Let's say I'm saying the source voltage is 3-phase source voltage is actually coming from here. Let's say phase A, phase B, and or I would say AS for source, BS for source, and CS for source. So obviously, if I say the induced voltage here is in this direction, if I connect the source, the induced voltage is in this direction. Obviously, this dot says that induced voltage in the secondary would also be in this direction. Okay. Similarly, for B phase, if it is here, the induced voltage would be in this direction. So, and we want to make the start point of it. What I will do is, I will short these points. Okay. So this is higher polarity potential. This is higher potential point, this one, and this is the lower potential point. So what I did is I just marked this one here. So these are the importance of dot as well, and we'll see how the dots connection are important in three-phase transformer as well. And I'll short it here. So obviously this is phase A, this is phase B, and this is phase C here, right? I have marked the connection with the dots, these bold dots. Okay, so that means these points are not connected, right? These points are not shorted here. A here, B here. So this point, the red one, which we have connected with red, that would be your neutral point. Let's say neutral point is, I'm showing with capital N here. So this point has become star point. What about this at the secondary of this transformer? So if you want to make it a star, you can easily make, obviously, so we know if we know the dots properly, then we can easily short these points. So here we have shorted A2, B2 and C2, right? So this end point is A2, B2 and C2. Similarly, if the dots here is appearing in the is at A1, okay, B1 and C1, then we should short A2, this we will short, okay, and from here you'll get the different voltages A, B and C, and this you can easily connect to the three-phase load. So here the polarities which are marked, this is A2 here, B2 and C2. So this neutral point at the secondary of it, it is here A2, B2 and C2, they are connected. Let's say the supply which is coming at the source, it is a positive sequence supply, okay. Positive sequence means VA, VAS is V at an angle 0, VBS is V at an angle of minus 120, and VCS is V at an angle of plus 120 degree. Okay. Then what would be the voltages appearing here? So the line voltages, if you'll see, because this I said okay, these are the phase voltages, but if you see the line voltages, obviously the line voltages would be root, if these are the phase voltages, then the line voltages would be root 3 times of it. Okay. And what is the voltage which is appearing at the primary of this transformer? It will have the similar phasor diagram, right? So I can easily draw the phasor for this primary side. Okay. So primary side, let's say if I am drawing VA capital, and if I am drawing per phase, either I draw the per phase voltages, the phase voltage phasor diagram, or the line voltages. I will see the phasors there. Okay. So let's say if these are phase voltages VA and here, then positive sequence means VB and would be at 120 degree to it. The supply is all balanced, then VBN would be 120 degree of it, and VCN would also be at 120 degree of it, right? So this is a positive sequence. So VAN, VBN, VCN. What about the line voltages here? Obviously, line voltages will lead the phase voltage by, in a positive sequence voltage, it will lead the phase voltage by an angle of 30 degree, and magnitude would also be higher than that. So this is your VAB. So I'm not drawing for the other phases for the sake of simplicity. Okay, so this would be at an angle of 30 degree, right? This was drawn at the primary side of the transformer. What would be there at the secondary of the transformer? So depending upon the turn ratio A, the voltage will appear there, right? On each, because A I have marked, A is to 1 I have marked for each phase. Okay. So obviously the phase voltage will be transformed as per the transformer ratio in the secondary of the transformer. And since they are, and we know that, let's say here, these, the voltage at the primary side, the phase voltage at the primary side and phase voltage of the secondary side, they are in phase. Let's say if it is an ideal transformer, they would be exactly in phase, right? So we will say that depending upon the turn ratio, the phasor magnitude would be different, but they will have the same phase angle. So this is your VAN, VBN and VCN. So what about the line voltage then? So the line voltage this time would be here, right? VAB. Okay. Just what would be the transformation ratio for the line voltages on both these sides? Okay. So let's say VL of primary is root 3 times of V phase, right? Line voltage of the primary side is root 3 times of the phase voltage, okay, of the primary, or I would say V line of primary with 1 and V phase for primary we will write with 1. Okay. And what about V line of the secondary? It would be root 3 times of the V phase of the secondary. So what is the this transformation ratio? VL1 upon VL2. The line voltage transformation ratio, if you see, it would be VP1 upon VP2. And already we know that VP1, if we say that this is the VP1 here for phase A, VP2 here for phase B, so obviously this would be A by 1. So the transformation ratio in a star connected connected circuit remains same. If we started with A turn, the per phase turn ratio is A is to 1, then the line voltage turn ratio remains same, that is A is to 1. Okay, and what is the relative angle between the line voltages? Let's say here the line voltages, the relative angle between the line voltages or either the phase voltages of both the sides, if you see, that is 0 degree. So sometimes this kind of arrangement is known as, star y. For star we generally write y. So we'll say that this is y 0 degree. That means the line voltages of the phase of the primary side and the secondary side, they are exactly in phase. Okay, they are written as like y means capital Y and then small y and then 0 degree. Okay, so remember this degree, this angle 0 degree is actually the angle between the line voltage of the primary and the line voltage of the secondary. So the relative angle between the primary voltage, either the line voltage or the phase voltage here, they would be 0. So this angle signifies that displacement. So how much angle variation is there in the primary line voltage and the secondary line voltages? Okay, if it is a balanced transformer, balanced 3-phase supply is coming, so this angle is actually 0 degree here. So here we have connected all the dots, which was the non-dotted end, A2, B2, C2. Let's say what will happen if you connect A1, B1, so this is B1 and this is C1, right? If you short all A1, B1 and C1 together, what will happen? So let's see that. So for a star-star connection only, let's say I am erasing this. Let's say this time what I am doing is I am connecting these ends. I am shorting it. All the dotted ends I am shorting. This will work. Obviously this will work. Okay. Now the transformer, how the line voltages will appear now. So you see, just try to write the phasor diagram for obviously the primary side phasor diagram is same, which is VAN, VBN and VCN. What about the phasors here? So this time if you'll see the voltage, if this is A here, B here and C here, and you have shorted and the neutral point is A1, B1 and C1. So this is A1, this is B1 and this is C1. So what will happen if A1, B1 and C1 we have connected? So how the voltages will appear here in, let's say, this phase A of the secondary side. Obviously this time, because we have shorted the neutral, so neutral is here, but this time VAN would be in this direction, opposite to the previous one, right? And what about BN? B1 would be in this direction. opposite to this, and CN would be in this direction, VCN and VPN. Okay, so if you see the relative angle between these two, of the primary and the secondary, and similarly it will go with the line voltages as well. So let's say this is, if this is the line voltage at an angle of 30 degree, for B the line voltages would be here, VAB, okay, at an angle of 30 degree here. Okay, so what we see that the relative angle between these two is exactly 180 degree opposite to each other, is 180 degree. They are at 180 degree to each other. So this connection we can say is as Y 180 degree. This was the case when we have considered star star. So can we make, let's say in the same configuration, let's say this time what I'm doing is, let's say someone decides, okay, I won't connect as per the notations. A1, like we said, okay, this is the positive terminal, this is the negative terminal, and I just want, because anyhow, how does the winding knows that which point of mine has been made as a star point or the neutral point? So what he decided, okay, what I will do is I will connect this neutral point, this the other end of it. So let's say this time what he decided, okay, A1 here and A2 I will connect to B1. So he decided, okay, I will connect it here, B1, and he decided, okay, see here, so C2 he has connected. So this is also a star point, right? This is also a star point. But now look at the phasor, how the line voltages are actually coming. What about the phase voltages? Let's say phase voltages will still have the same voltage here at the secondary, VP1, VP2. As per the turn ratio, the same voltage will appear here for transformer A, for transformer B, for transformer C as well. Now the turn ratios remain same, primary side voltages remain same. So same voltages will also appear here. So what's the problem if I short it here? So let's see. Sorry. B he has connected here. I have made a mistake here. So B point, B1 was made as a neutral, and this is B here, and this is C here. So obviously the primary side, if you draw the phasor diagram, it will remain same. Okay, VAN, VBN for positive sequence. This will be the sequence VCN. Okay, so the primary side positive sequence is same phasor, but see about the secondary side. So VAN would be in phase with, see here, VAN, this is the neutral point. So VAN is in phase with this voltage, right? So this is VAN. This is the neutral point. What about VBN? So VBN this time, this is the voltage difference, right? The opposite of VBN would be opposite of this voltage, right? Of the primary side. So VBN would be opposite to this. So opposite to this means it would be here, VBN. Okay. And what about VCN? So VCN, if you see, this is the neutral here. This is the voltage direction. So what about VCN? So obviously VCN would be same as this one, right? Here VBN, if you'll see, VBN would be this voltage, right? VBN would be this voltage. So this VBN is actually opposite to the voltage what was induced there, right? So I can say that means what was there at the primary side. So VBN here and VCN would be here in phase with this voltage. So if you measure between VAC, you will get proper line voltage, no problem. AB will have only this much difference, right? And even line BC, AB will have different voltage, AB and BC. So you'll get a unbalanced supply at the load, at the line voltages here. Though the phase voltages are balanced, the magnitudes are balanced, okay. So if you measure individual phase voltages, you will say, okay, no problem is there. But if you measure the line voltages here, the line voltage would be different. Since this was a star connected one, so we saw that, but there is not so much of problem. And we'll see if it is a delta connected circuit, or if a delta connected circuit, we have to ensure that the terminal voltages are properly marked. Okay, it should be proper dot. We should ensure that the dots are properly connected. Otherwise, it will create a short circuit. We'll see that, and it may even damage the windings. Okay, so we'll say that in a delta connected circuit. So next we will talk about delta connected circuit. So in a star connected circuit, the transformation ratio, what was there in the per phase, the transformation ratio of the each phase, the same transformation ratio was appearing at the line voltage as well. Okay, so transformation ratio of the phase voltages and transformation ratio of the line voltages of primary and secondary, they are same, A:1. And we'll see for the delta connected circuit as well. But this star connected circuit has some other severe problem, which we will take up when we will discuss about harmonics and these things for three-phase transformer. Okay. Now we'll talk about delta connected circuit. Before moving further, we'll see how these are becoming a star, right? So I'm just drawing the simple version of it. Okay, just to simplify, I will just draw the transformers connection here. So let's say for transformer 1 or transformer A, this is the primary winding. Okay, so this was A1. I'm drawing for this connection. Okay, A2, then this A2 was connected with B2. Okay, so B2 here, and this is B1, and then this is C1. And here this is A2, B2 and C2, and these are all neutral point of the primary side. Similarly for the secondary side, if you'll see, so this is your, here what I have done is, if I'm drawing for this, so you can see that A1, B1 and C1 I have shorted, right? So A1, this is your A1, and this is A2 here. Similarly here, this is B2 and this is B1, and here C2 and here C1. This is the neutral point. If you exactly see here, if A1 was in this direction for primary, okay, for secondary this would be towards this direction. That's how for this connection we have got a reversed phasor diagram here. Okay, now we'll discuss about delta delta connection.